This will be part 2 in this recap of creating and using a memory, from encoding to storage to consolidation and retrieval. Now in part 1, we saw what it looked like when the brain is encoding and storing and then retrieving soon after learning. In this lesson, we'll focus on this all-important process of memory consolidation. And this will be the answer to the question, how are cortical memory traces strengthened? You'll recall we were left with a brain with weak cortical memory traces, but a strong hippocampal memory trace. Well, how are the cortical memory traces strengthened so that we won't need a hippocampus to retrieve them? The answer will be memory consolidation. And here's what scientists think is going on. When we go to sleep, this process is happening during sleep. The hippocampal memory traces are reactivated, and they signal the linked cortical memory traces to strengthen their synapses. So the hippocampal memory traces are activating the neurons in the memory traces in the cortex, and those activated neurons then will be triggered to grow stronger synapses. We're going to call this hippocampal replay. It's as if the hippocampus is replaying the memories that were formed that day. And the purpose of that, again, is to integrate the day's learning into the long-term storage system in the cerebral cortex. Now, you'll recall the analogy that memories are like writing on paper, so by applying more ink, we're increasing the strength of the memory trace. In this sense, then, the analogy is the hippocampus is like a printer of memories to the cortex. So the process of memory consolidation is this communication between the hippocampus and the cortex. The hippocampal memory traces are going to be reactivated to strengthen the cortical memory traces. That's memory consolidation, and we're using a printing analogy. So during hippocampal replay, then, it's like the brain is applying more ink to those cortical memory traces. In fact, the hippocampal neurons accelerate their firing by a factor of 20, so a single learning event can be replayed hundreds of times during sleep. Now let's take a moment to do a side-by-side comparison between what we just saw occurring in sleep versus what was happening during the encoding stage, learning the original event. During the encoding stage, it's the cortex that is signaling the hippocampus. The hippocampus is making a memory trace that represents the cortical activity. When we go to sleep, the flow of information is in the reverse direction. The hippocampal memory traces are now activating the cortical memory traces for the purpose of strengthening those cortical memory traces. So we have the reverse flow of information during these two phases. The learning phase, it's from cortex to hippocampus, and during consolidation, it's hippocampus to the cortex. Notice also that during sleep, the flow of information resembles that which occurs during memory retrieval. You'll recall soon after learning, the cortical memory traces are weak because there's low plasticity neurons in the cortex there. But the hippocampal memory trace is strong. And so soon after learning, we need the help of the hippocampus to reactivate those weak cortical memory traces. Well, when we go to sleep, it's those strong hippocampal memory traces that are activating the weak cortical memory traces so as to strengthen them. They will get strong enough, hopefully, so that we won't need the hippocampus anymore for retrieval. Now, before I show you the evidence that hippocampal memory traces are reactivated to strengthen cortical memory traces, we first need to learn about some special cells in the hippocampus called place cells. In this animation, we're going to see a rat exploring its environment. And as it does so, scientists are recording from individual hippocampal neurons, a certain population of these hippocampal neurons. So here's one of them over here. Every time the neuron makes an electrical signal, scientists can record that electrical activity. What they found for certain hippocampal neurons is the neurons seem to be sensitive to the location of the rat in its environment. Notice the little pink dot means that the hippocampal neuron became electrically excited when the rat entered that location. So because that particular neuron seemed to become active only when the rat was at a certain place in its environment, they were called place cells. Other hippocampal neurons would become activated when the rat was at a different location in space. And the particular region in space that activated a particular hippocampal neuron was called the place field. So as a rat explores its environment, you're going to get different hippocampal neurons becoming activated depending on where the rat is in its environment. So in this animation, we see a rat moving back and forth along a corridor. And if you're recording from multiple hippocampal place cells, you'll see a sequence of activation of different hippocampal place cells as the rat makes progress along this corridor. So scientists can record the sequential activity of hippocampal place cells, and that becomes a record of the rat's movement in space. Now, what's the evidence that the brain goes through this process of consolidation during sleep? Well, consider the following experiment. Here we have a rat that's going to make its way down some portion of a maze, let's say. Now, meanwhile, scientists have inserted electrodes into the brain of the rat, down there into the hippocampus, into a population of neurons called place cells. And here we have 7 different hippocampal neurons that are being recorded with electrodes. Now, these place cells seem to be neurons that are keeping track of the animal's location in space. And each particular neuron will be activated when the animal is in a particular place. So neuron number 7 got activated when the animal was at this location in the maze, but as it moved further along, neuron number 7 turned off and neuron number 6 became activated. And then as it continued to move down this path, you see the activation of neuron 5, 4, 3, 2, 1. So there are populations of neurons in the hippocampus that are keeping track of the location of the animal, and scientists can record from all of those neurons, and you get a pattern of activation depending on where the animal is in its environment. Now in this video, we're actually going to see a rat moving along through a maze here, and we'll see a record of activity among those hippocampal place neurons. If you hear those little clicks, those would be electrical signals being generated by individual hippocampal place neurons. And here we see a visual record of the activity of different hippocampal neurons. And they're color-coded. So when it was in this section of the maze here, the one neuron, color-coded blue here, became activated. But as the rat moved along, it was a different hippocampal neuron that got turned on. So the point is, though, you can sort of make a record of the pattern of hippocampal neuron activity as the animal explores its environment. And then you can simply let the animal go to sleep while you're still recording from those same hippocampal neurons to see what happens. So now, again, on the left, we saw the pattern of neuron activity when the animal was learning about its environment, moving through the space. Look at what happens when the animal goes to sleep. We have the same neurons are being reactivated in a similar pattern of activity. So again, the electrodes were still in the animal's brain when the animal went to sleep. So you can just follow the activity of those neurons during sleep, and we get the same kind of pattern of activity. So the rat hippocampal neurons activated during a learning event are later reactivated during sleep. So this is evidence for this hippocampal replay idea. So during memory consolidation, then, the hippocampus is acting like a teacher. It's going to be teaching the cortex to strengthen those memory traces. So by day, the hippocampus is a learner, and by night, it's a teacher. Using our computer analogy, the hippocampus is writing data to the hard drive, the cerebral cortex. And during this process as well, cortical memory traces can be linked together, forming a unified sort of network of memory traces that represents the learned information from that day. So this high level of activity during memory consolidation creates the ideal conditions for synapse growth and memory trace connection. And you'll recall that we need to make those connections between memory traces in order to build concepts. So the concept of a tiger includes what a tiger looks like, stored as a memory trace in visual areas, what a tiger sounds like, stored as memory traces near the hearing area, what a tiger feels like, stored as memory traces near the touch area, and the sound of the word tiger and other related facts about tigers, which would be linguistic, so words and their meanings. Well, the brain will link all of those memory traces together, sort of a hub of memory traces linked together, and this is what we would say is the concept of tiger stored in the semantic memory system in the cerebral cortex. Now, strong cortical memory traces can be retrieved without a hippocampus. So when we go through consolidation during sleep, we're setting up the condition where we're strengthening the cortical memory traces so you won't need the hippocampus to retrieve that information. Rather, frontal cortex retrieval systems can successfully locate and reactivate those memory traces. And as we'll see in the final part of this lesson, it's important to do this consolidation of memory traces in the cortex because there will be changes happening to the hippocampus. The hippocampal memory traces are going to be erased in preparation for new learning, but we'll get to that in a moment. Let's do a quick recap here. The encoding and storage stage, we've got cortical regions responding, the hippocampus is responding, and in all those locations we have memory traces being made. When we go to sleep, we activate those strong hippocampal memory traces to strengthen the cortical memory traces. And with respect to retrieval, if it's weak cortical memory traces we have, because it's soon after learning, we're going to need the hippocampus to assist in the reactivation of those memory traces. But if we've already done lots of consolidation and we've got strong cortical memory traces, we don't need the hippocampus. The retrieval systems in the cortex can find and access and activate those memory traces. Notice what happens if we don't have a hippocampus. Over here, we won't be able to make a memory trace that links together the cortical memory traces. With respect to retrieval, we won't have a hippocampus to help us reactivate those recently made weak cortical memory traces. And then we won't be able to produce new, strong memory traces in the cortex because we don't have a hippocampus that is what drives the consolidation process. So with no hippocampus, we can't strengthen cortical memory traces. We'll end this part of the lesson with an answer to the question, why does the brain consolidate memory in the cortex? Why go through this process during sleep of firing up the hippocampal memory traces to strengthen the cortical ones? And one answer can be seen by just counting the neurons in these two structures. The hippocampus has roughly 50 million neurons. That sounds like a lot, but not compared to the cerebral cortex, with something like 16 billion neurons. Now here we're just highlighting a section of the cortex. All of this here is cerebral cortex. All of this here. And so there are just vastly more cortical neurons, and so more synapses. So you have a greater storage capacity for memories traces in the cerebral cortex. So we want to say that the hippocampus then has a small memory capacity, the cortex a large memory capacity, and that would be one reason for doing memory consolidation, that we just can't store all of the stuff we learn for our lifetime in the hippocampus. It's got to be stored in the cortex. But we're going to be using those fast learning neurons in the hippocampus to make good, strong memory traces. We will use those strong memory traces of the day's learning to strengthen the cortical memory traces for that same information. So we're integrating the day's learning into the long-term memory system in the cortex. The hippocampus is a fast learner by day to be a teacher at night. Now there's another reason that we have to do this consolidation process, and that's because of the low capacity system here. These hippocampal memory traces, they have to be refreshed, they have to be erased to prepare the hippocampus for new learning. So there are two phases of sleep that we need to understand. During the first phase of sleep, we do the memory consolidation. We strengthen the cortical memory traces. But then, because the hippocampus has limited memory capacity, we're going to need to erase those memory traces in the hippocampus to prepare the hippocampus for new learning. So newly formed memory traces must be saved to the cortex before they are erased in the hippocampus. So this is another reason why we have to do this consolidation process to keep the hippocampus ready to learn. And we can see that in a diagram like this. Here we have the hippocampus before learning. We've got a bunch of hippocampal neurons with weak synapses. They're ready to go. Remember, learning involves strengthening of synapses. So you want to have weak synapses to begin with. After learning, we have strengthened a set of those synapses. But the problem is these are high plasticity neurons. That's good on the one hand, but on the other hand, one learning event can max out the synapse strength. So these synapses cannot be strengthened anymore for further learning. So the storage space for new memory traces has been reduced. So notice, as these synapses have been strengthened, it means that there are fewer neurons in the hippocampus capable of new learning. Well, as time goes by during the day, we're learning more and more stuff. All of the other synapses will be strengthened as well, and you'll reach a point in the hippocampus where you're at synapse saturation. If you can't strengthen any more synapses, then the hippocampus cannot learn anything new. And the way the brain seems to have solved this problem is sleep, that second phase of sleep, where the hippocampal synapses are weakened again in order to prepare the hippocampus for new learning the next day. So this is this refresh. Sleep is going to refresh the hippocampus, and by doing so, it's effectively erasing the memory traces that it made during the day's learning, and then erasing those memory traces to prepare the hippocampus for the next day's learning. The hippocampus then, the memory traces we would say have fast decay, and that's a feature, not a bug. We need to erase memory traces in the hippocampus so it's prepared for new learning. By contrast, the cortical memory traces have slow decay, and that makes sense for a long-term memory system. So let's compare the hippocampus side by side. For the hippocampus, we have fast learning and fast decay. Cerebral cortex, slow learning and slow decay. Now, these are features of these memory systems, not bugs. So again, on the hippocampus, the fast learning is excellent. We can make good, strong memory traces that will be used for consolidation, but then we need to weaken those memory traces to prepare for new learning. Whereas in the cortex, it's a slow learning system. And this, by the way, is why we have to study repeatedly. We have to repeatedly activate cortical neurons, go through multiple rounds of memory consolidation to get those synapses really strong. But once we get them strong, there is slow decay. And that's good for a long-term memory system. This then completes our tale of creating and using a memory, from encoding to storage to consolidation and retrieval, and the critical role for the hippocampus.